So this is a fourth and final video on G inverse. So you already seen that there are three types of G inverse. One is reflexive. So what is G inverse? A G A. G inverse of A is G. So A G A equal to A. This is the definition of G inverse. And reflexive G inverse, if G A G is also G. That means if G is a reflexive G inverse of A, then A is the G inverse of G. A is the G inverse of G. It may so happen that A is the G inverse of G, but G is the not G inverse of A. But if A is reflexive, then if A is the G inverse, reflexive G inverse of A, G is the reflexive G inverse of A, then A is the reflexive G inverse of G. And then there is a idea is called minimum norm G inverse. I mean, what is minimum norm G inverse? For any y belongs to the column space, that means the Ax equal to y as a solution, then x equal to gy is a solution, and the x equal to gy is a solution of this. So we know if G is a G inverse, then y equal to x equal to gy is a solution. But for the minimum norm, this is the this solution is a minimum norm. This solution has a minimum norm. So what is the meaning of the minimum norm? That solution gy has a minimum norm. Than other what are the other solutions? The other solutions are gy plus 1 I minus ga z, for any z. For any z, gy plus I minus ga into z. This is a solution for Ax equal to y, and gy is the one solution, and g is the minimum norm. If this is happen for all z, it's true for all z. So if you take any other solution is of the form. This is a solution, and any other solution of this form. So this is a set of all solutions. If you just change your z, you will get the all solutions. You have to take the suitable order. Z is arbitrary, but you have to take the suitable order such that this is defined. So this is a minimum norm G inverse. This is the one is the definition of the G inverse. Two is the definition of the reflexive G. 1 and 2 is reflexive G inverse. 1 and 3 is minimum norm G inverse. And we know we prove it that this is if and only if this has GA is a symmetric. So GA transpose is equal to GA. So, and the fourth one is least square G inverse. And least square G inverse is, what is that? This is a least square G inverse. G is least square G inverse of suitable order. Least square G inverse, least square or least square norm. Some least square norm. Norm is the square of the norm is the least. So least square norm G inverse of A if AG transpose equal to AG. But this is just definition, and the idea is this. This is if and only if this equivalent condition is that for all a and x and y, AGY minus y. Here remember that for minimum norm, that y must be belongs to the column space. But here we may take any y, obviously for the suitable order. That means gy may not be the solution. So if gy is not a solution, then agy is not y. If gy is a solution, then agy is the y. So agy is y, so y minus y, this is 0. The norm cannot be negative, so this is 0. But still, if it is y is whatever, if y is a solution, y is in the column space of A, then agy minus y is 0 for all y. So then every this minimum norm property satisfies every g. But now y is not in the solution. Y is other outside the column space. Then agy is not equal to y. So then in that case, this is the this norm is not negative, not 0. This is strictly positive. But you have to take such a g, that g is actually least square G inverse. For that g, whatever the y may be. It may be column space or the outside the column space. It's column space actually this is trivial. If it's outside the column space, then it is positive, but still it is less than or equal to AGY minus y plus AW, where W is that just you can write in this form. You can just in this form AX, right? It's better. You just write AX minus y. So if you take any other solution that x as for any xy, if you take any other x other than gy, this norm cannot be less than. So that for that particular gy has this minimum least square norm. So this is this AGY is a closest to the y. Remember that this is like that. So this is the column space of A. So this consider this as a column space of I, which is a subspace of whole vector space or n or whatever. Now it is in R3. Now take y is outside that, outside the column space. Then we have to take the such a list. You can take the list thing in gy. Remember that AGY in the column space of A. Remember AGY is a column space of A because AX equal to AGY has a solution. That's a solution. The solution is x equal to gy. So this is a solution. So ax equal to AGY has a solution. That means AGY is in the column space of x, and obviously it is AGY is a column space of x A because it is just A into something. A into something is a column space of A. A into some vector is a column space of A. Now this is the column space of A. Now we have to take such a element of the column space. AX also in the column space of A. Here AX is also column space of A. But we are taking that AX, that is AGA, AGY, which is the closest, that the difference between this is the distance is the norm of this is AGY, and you take any other x. This is AX. Now this norm will be bigger than that y norm. This norm is the distance between y and AGY. So this is the idea. You have to find the closest point of column space of A, which is closest to y, for which value of for what value of x actually. That x is the gy, because any element of the column space of A is of the form AX. Now the special value of that x, which is actually gy, this is the minimum closest to y, and for that value of g, that which value of this occur, that g is called the least square g inverse. This is the idea. Now the in figure we already got this, that that gy will be such a thing that AGY, this must be perpendicular to the y minus AGY. If AGY is a perpendicular to the y minus AGY, then by Pythagoras theorem we got this. This is because this is actually the perpendicular foot of the perpendicular. This is a projection of that y vector in column space of A. That is the idea. We have to prove that for this special type of G inverse, that y minus AGY, that y minus AGY is that red vector, and the red vector. This is y minus AGY. This red vector is y minus AGY. That vector is perpendicular to AGY. We have to take such a x. X is here in gy, for which that AX and this y minus AX must be perpendicular. And for fulfill this condition, x must be some gy. So this is the idea. So what is the proof? The proof is going like that. So we have first proved that if AG transpose is equal to AG, then this will be have the minimum. So this implies that for all x, y, in whatever suitable order. This a g y minus y, this norm is less than a x than that norm. So what we have to prove? So let this we have to prove. Now put y x minus gy. That is the idea, that x minus gy. So x minus, then you have to multiply by a. That will be this. This will be this thing. This is actually this. We take this as a proof vector. That proof vector is nothing but a into x minus gy. So put that as a z. So this is az actually. W. So now what we have to show? We have to show that what is ax? Ax now agy plus aw. So to show, we have to show that norm of agy minus y, that must be, that is less than or equal to agy minus y plus aw. So that we have to show. That is the aw vector. So this is this red vector is agy minus y plus w. That is actually that diagonal thing. That must be bigger than that agy minus y, and that will be true if this is a perpendicular. Basically, this red vector is a perpendicular to the whole space, so orthogonal basically. So that means it's a perpendicular to the blue vector. Once I show that it's a perpendicular to blue vector, then using Pythagoras theorem, we can easily show that this is the hypotenuse is bigger than this one side. So this is the idea. So you just remember this figure. Always you have to recall this figure. Now what we have, so we prove that like a Pythagoras theorem. So we have to take that square of the norm. So that square norm, we will take the square of this. And now what is this? This is inner product between this. Remember, you can directly use the Pythagoras theorem because in the inner, we are in the inner product space. So it's an inner product space. So we have to take this is, there is a one similar theorem like Pythagoras theorem in R2, it is, or R3, it is called Parseval identity. We actually want to use that Parseval thing in inner product. So this is inner product. So inner product of a plus b with a plus b. This is, you take one vector and this is another vector. So a plus b plus inner product a plus b. So it is a inner product a. So like a dot a, which is the again norm of that. So agy minus y norm square. Then aw inner product, which is norm aw square. Now there is a product term, twice ab term. So twice inner product of agy minus y to aw. Now inner product is dot product. So it is like a dot b or j dot product. So it is a, in vector form, it is a just a transpose b. Inner product of two vector is just a transpose b. So remember, this inner product is a real number because norm is a real number. Now just we have to show this product term is 0. Once I show that this product term going to 0, then it is actually we have to show this because we in the figure, just we call this figure that aw and agy minus y is a perpendicular. So we have to show this is an inner product is 0. Once I show that inner product is 0, so we are done. We are done because this will be then agy minus y, that inner product norm square to aw square, but this is less than or equal to norm of this. So norm cannot be negative. That square cannot be negative. So this is the idea. So we can now we will show that this. Now we have to show that the product term is 0. So how do you show that the product term is 0? So what is the product term? So this product term is agy minus aw. This is actually agy minus y transpose aw. That is actually equal to the whole transpose because it is a real number. Since it is a real number, if we take the transpose, that this will be the same as that. So it is actually aw transpose agy minus y. Now this is W transpose A transpose, then it is what? This will be AG minus identity y. Now you just take into the inside that W transpose what? A transpose, but what is AG? By definition, we assume that AG is AG transpose. AG is AG transpose. So this is AG is actually AG transpose. This is, since it is a by definition. So this is G transpose A transpose. So this is A transpose G transpose A transpose minus A transpose Y. Now A transpose G transpose A transpose. What is that? This is actually A G A whole transpose, and this is A transpose. But AGA equal to A because it is a G inverse. Since it is G inverse, AGA equal to A, so it is 0. So you have this. So you got this this product term is 0. So once I assume that AG equal to AG transpose, we have this. This is a least square thing. Now we have to show the other way. For in this is a least square thing, then it will be. So we have to show that for all xy, if this norm is least, this norm is least, then it implies that AG transpose equal to AG. That we have to show. Now again, we just for any vector, since it is any vector, so set y equal to ax, take y equal to ax. So if we take y equal to x, what happens? Then AGAX minus ax is less than or equal to 0. We put y equal to ax because it is true for all xy. So takes that y equal to ax. Now some norm is 0 means that the vector is 0 actually. This vector is 0. So this equal to x. Now this is true for all x. Since it is true for all x, we know if ax equal to bx for all x, then a equal to b. So then ag equal to a. So this therefore g is a g inverse. G is a g inverse of g of a. So we have this thing that g is a g inverse. Now next we have to show that ag transpose equal to ag. Now how do you prove that this this will be AGA equal to AG transpose equal to AG? That we will prove in the similar like the previous theorem for this minimum norm G inverse. We proved in the previous video that if it is some solution of AG AX equal to Y is with a minimum norm, then it is a that minimum norm G inverse. We have to use that, and we use this thing in a similar way. So now we have this G is a G inverse of A. Now since G is inverse of A and Y belongs to some in the column space, because Y equal to AX, Y is in column space, and put that G equal to Y equal to GY. Now this is a solution of AX equal to Y. Now since G is a G inverse, then what we can, how do you show that? This is Okay, just take as an exercise. I'll discuss in the next class. So take as a homework. I have to think little bit on that. So why this is a why this is a that AG transpose AG. Okay. Go to the next theorem. Next theorem is this. Now we will discuss on Moore-Penrose G inverse. Moore-Penrose inverse, or it is not G inverse, Moore-Penrose inverse. What is Moore-Penrose inverse? We know this Moore-Penrose inverse has satisfy all three conditions: reflexive, then minimum norm, and least square. So that means it is AGA equal to A. Second condition, reflexive GA equal to G, and the third condition is AG transpose equal to AG, and the fourth condition is GA transpose equal to GA. This all four conditions hold simultaneously, then it is called Moore-Penrose inverse, and we will show that Moore-Penrose inverse exists, and this is unique. So it is reflexive and both minimum norm and least square. Then it is Moore-Penrose inverse, satisfy all these four conditions. Now we will show that this exists and it is unique. Now we will show that it is unique first. So why it is unique? Why it is unique? Uniqueness. If there are two Moore-Penrose inverse, then they must be equal. So let G1 and G2 two Moore-Penrose inverse. Moore-Penrose inverse. That means G1 satisfy all four conditions and G2 satisfy all four conditions. So that means A G1 A equal to A, G1 A G1 equal to G1, A G1 transpose A G1, and G1 A transpose A G1 A. Similar for the G2. Now we have to show that G1 equal to G2. So this is slightly technical. So first start with G1. So G1, what is G1? G1 is G1A G1. G1 is G1A G1. G equal to GAG, since it is reflexive. Now we just club this thing, AG1. Now what is AG1? What is AG1? AG1 is AG1 transpose. So this is AG1 transpose. What is that? We know this is G1 transpose, A transpose. Now we just change that A transpose. What is A? We just replace that A. What is A? That A is G1 transpose. You just A, what is A? Now use that G2. A equal to A G2 A, because G is G inverse. G2 is the G inverse transpose. Now what is that? G1 transpose, A transpose, G2 transpose, A transpose. Now we club G2 transpose A transpose. We want to replace that. This is what? This is G1 transpose A transpose, then G transpose A, that is A G2 whole transpose. But A G2 whole transpose is AG2. Is AG2, because G2 is that minimum norm. This is minimum norm or least square. So what is least square? We have this G1 equal to G1 transpose A transpose AG2. Now we club this part, G1 transpose A transpose. What is that? This is nothing but G1 A G1 transpose A G2. But this is A G1 transpose A G1. This is A G1. A G1 A G2. Now take that A G1 A1. A G1 A1. What is that? We know this is G1. This is A, because G1 is the G inverse. So G1 A G2. So it is A1 G1 AG2. So G1 equal to G1 AG2. Now again we use that A. Break this A. Break this A to G1 A G2 A. G2. A is A G2 A because G2 is a G inverse. Now we take that G2A. Now what is G2A? G2A is G2A transpose. G1 A G2A. So G2A is G2A transpose. What is this? G1 A transpose G2 transpose G2. Now club this now. This part G1A. Now what is G1A? Again G1A is G1A whole transpose. A transpose G2 transpose G2. Now G1A transpose is A transpose G1 transpose A transpose G2 transpose G. Now we take that A1 A transpose G1 A transpose. What is that? This is nothing but A G1 A whole transpose and G2 transpose G2. Now what is that? That is just G1. This is G1. Oh sorry, this is A. So it is A transpose G2 transpose G2. Now what is A transpose G2? This is G2 A whole transpose. But what is G2A? G2A is nothing. G2A transpose is just G2A. It is G2A. G2A G2, but G2A G2 is just G2. So G1 equal to G2. To prove it that G1 equal to G2. So that means if it is if Moore-Penrose inverse exists, then it is unique. Now, how do you show this Moore-Penrose inverse exists? By the way, we use that A plus as Moore-Penrose inverse of A. Whatever A may be, it may be null, maybe whatever any or non-square matrix, whatever may be, that Moore-Penrose inverse always exists, and it's unique. To show that it exists, this is the last thing to show in G inverse, that we know A has a rank factorization, B that say rank factorization is B into C. We know there is a rank factorization of matrix, that rank factorization of this matrix A equal to BC. Now this is the rank factor. The Moore-Penrose inverse of B is just B transpose B. Now B transpose B is a full, since B is full column rank and C is full row rank, that means B transpose B is non-singular. B transpose B is non-singular. So remember that B has, since the rank factorization, B has full row rank, full column rank, and C has full row rank. Or the other way, what is the rank factorization? B transpose B. So B transpose B. No, it is a full row rank and C is the full column rank. What is B transpose B? That means your B transpose like that. So the number of column may be bigger than that. B is like that. So B transpose B in the smaller square, small square. Right. So B transpose B. That means your B is so right. B is the full row column rank, and C is the full row rank. Now B transpose B is a full column rank. That B is a full column rank. That means B transpose B is the non-singular. That means the inverse exists, and that inverse is this B transpose B whole inverse. Then take B transpose. This you can prove that this is a G inverse. That is Moore-Penrose G inverse of B. This is a Moore-Penrose G inverse of B. And C similarly C Moore-Penrose G inverse of C is C transpose C transpose inverse. So C transpose is again non-singular matrix. C transpose is a non-singular matrix, and C transpose inverse exists, and C transpose C transpose whole inverse. This is a Moore-Penrose inverse of C, and the Moore-Penrose inverse of A is just C Moore-Penrose inverse Moore-Penrose inverse of C into Moore-Penrose inverse of B. Now, for any A, B, and C exist, is a rank factor always exist, and that B plus and C plus exist, and we can just check why this B is a Moore-Penrose G inverse. Sorry, Moore-Penrose inverse of B, and why this the C plus B plus is the Moore-Penrose inverse of B A. So what you have to check. So first you have to check that this A plus is the G inverse. So to show that, we have to show A plus A must be A. Then how do you show this? So A is BC, then it is C plus means C transpose, C to C transpose whole inverse, that is a C plus, and then we have to take the B plus. What is B plus? This is B transpose B whole inverse, B transpose, and then we end with the A. A is again BC. Now we got this. We have C transpose inverse with multiplied by C transpose. So it is identity. Similarly, B transpose B with multiplied by B transpose B inverse. So it's identity. So it is end with B identity C. So it is BC. So it is A. So A plus is the G inverse. Now we have to show it is a reflexive. So to show reflexive, we have to prove that A plus is A plus. So what is this? This is A plus is C plus B plus. So C plus B plus means C transpose C transpose inverse. This is C plus. Then we have to take the B plus. B plus is B transpose B whole inverse. Then B transpose. This is we take B plus A plus. Then we have to take A means BC. Then we have to take again A plus means C plus B plus. C plus is C transpose C transpose whole inverse. Then B transpose that B plus is B transpose B inverse. Then B transpose. Now what? This is identity. This is identity. This is identity. So we have C transpose C transpose inverse, then B transpose B inverse, then B transpose. Now this is C plus. So this is C plus, this is B plus. So C plus B plus, so it is A plus. So we proved it is reflexive. Next we have to show that A transpose A plus transpose is A plus. We have to show this whole transpose is actually A transpose. And how do you show this? So this is nothing but A means BC, and A plus is C plus B plus. C plus is C transpose C transpose inverse, then B transpose B whole inverse, then B transpose, then whole transpose. Now this is identity. This part is identity. So that means it is B transpose B inverse B transpose whole transpose, which is actually B, that B transpose B inverse, then whole transpose, then B transpose. Now this is, we know A inverse transpose is A transpose whole inverse, so it is B transpose B transpose, then inverse, then B transpose, and then what happened? Then it is just again it is a B transpose B whole transpose B transpose. What is this? And this is actually equal to this thing, this part. So this is A plus. This is that, this 2%. So similarly, we can check that the rest is again the similar, that A transpose A plus A whole transpose must be A plus A. You can easily check it. So that means this is a Moore-Penrose inverse of A, that thing. And you can just actually check that B plus is the G inverse of B. That also you can check. Similar for C. Just check one. B plus is B transpose B whole inverse B transpose. So B plus is B transpose B whole inverse, then B, right? B transpose B whole inverse, then B transpose. We have to check that that is a Moore-Penrose inverse of B. To show that, we have to check B plus B is just B. So B, this is B transpose B whole inverse, then B, what? B, this is B transpose, sorry. So this is plus, right? So this is B transpose, then B, well, but this is identity, so this is B. This is identity. B transpose B whole inverse, B transpose B. So we have this, and similarly you can check that B plus is B plus. What is that? This is B plus is B transpose B whole inverse, then B transpose, then B plus. But this is identity. So actually B plus B is identity. Oh, B plus B is identity. So this is B plus. B plus B is identity. So that means easy. B plus B is identity, so it is B. B plus B is identity. That means B. It is B plus. Now, what we have to check? We have to check B plus B. That is identity. So that transpose is also identity. So this is identity. So identity transpose is identity, which is B plus B. Similar. Oh, then we have to one more checking that B plus is may not be identity. Oh, B plus. What is that? That transpose. You have to take the transpose of that. Is it B plus? What is B plus? So it is B transpose B whole inverse B transpose, then whole inverse whole transpose. So it is again it is just symmetric matrix. So it is B transpose B whole inverse, then that transpose, and that B transpose, and this is just interchange that transpose and inverse, and that is B transpose B is symmetric, so it is B transpose B inverse B transpose, which is nothing but B plus. So we have all this thing, and easily you can check the other thing for C. So this completes the everything about the G inverse, and one thing is just left out for checking that we have to check that homework as that if it is a list square thing, then it must be GA equal to G, AG transpose equal to AG. That as a left as exercise. So this complete G inverse lecture.